Hi folks, my name is Stuart Hill and I'll be your guide for this module. This is the first of a series of modules in which we will introduce you to the concepts, technology, and functionality provided in the GE JunglePax platform. In this module, we will be reviewing networking terms and concepts. For Ethernet, we'll look at the network interface and how it's defined. We'll look at packet construction. VLANs and spanning tree will be reviewed. Then we get into packet addressing and packet forwarding. Finally, for Ethernet, we look at traffic management. For MPLS-TP, we look at abstraction, packet construction, packet forwarding, prioritization, so QoS, and OAM. Let's start with the network interface. What is it, and how does it affect packet construction? Please note that while TDM interfaces are supported on the JunglePax as well, this module will focus on Ethernet for the examples discussed. The Ethernet port on a network device connected directly to an end user device is referred to as the UNI, the User Network Interface. The Ethernet port on the network device that connects to other network devices is referred to as the NNI, the Network-to-Network Interface. The device plugging into the network, typically a PC, laptop, or other end-user application device, like the GE L90, has one end of an Ethernet cable plugged into its Ethernet port, and the other end plugged into a network access device like the GE JunglePax. The application running on the end-user device generates Ethernet packets and sends them into the network towards a remote endpoint participating in the same application. The remote endpoint, depending on the type of application, will either generate acknowledgement packets or other Ethernet packets to return to the local endpoint as part of the overall conversation between the two endpoints. The network is comprised of switches and routers and transports the Ethernet packets. Specific data within the Ethernet packets is interpreted in order to be able to forward the packets to the appropriate remote endpoint and apply any necessary service quality treatments indicated by prioritization data, which is also embedded within the packets. When an application runs on a device, a series of protocols are employed to package up the information needed to be exchanged between the device and the remote endpoint of the conversation. These protocols are referred to as layers in the overall process of packaging that information for transmission. Data from the application is further augmented with data from each descending layer before ultimately being sent out into the network. Presented here are the 7 layers of the OSI, or Open Systems Interconnection Communication Model, commonly referred to as the 7 layers of the OSI stack. Each layer represents a distinct and unique component required to process and encapsulate datagrams for communication between network-attached endpoints. As an example, all 7 layers of the OSI model are employed to get information to your desktop web session from the web server on the Internet. When thinking of the OSI model, picture flowing down the stack for packets being created and sent out to a remote endpoint. Picture flowing up the stack from layer 1 to 7 for packets being received. Follow along with the reference model in the right panel as we do a quick walk down the OSI stack layers. The application layer is the program itself, like Internet Explorer, Safari, Chrome, etc. The presentation layer is the bits and pieces, like JPEG pictures and MPEG movies, pulled together to make the page. The session layer is the higher level communications protocols used to create communications sessions between your local workstation and the server for retrieving each of those pictures and movies. The transport layer manages those sessions with mechanisms to ensure reliable reception and provides other session tracking features as well. The network layer is the layer where the necessary addressing functions occur. Think of this as applying an address to an envelope prior to posting, or reading the address on an envelope just received to ensure it's for you. The data link layer is the layer responsible for actually sending the data across the physical network links. What is a VLAN? What is this thing called a spanning tree? Let's find out. A traditional switch hosts a single local area network, or LAN. Sometimes multiple separate LANs are called for in a single location, and it's just not justified to buy a second switch. A VLAN can be used to create multiple LANs within a single switch. A VLAN is a virtual local area network, assigned a numeric value between 1 and 4096. Each VLAN is a self-contained broadcast domain. Broadcast packets are only relayed within the VLAN in which they're received. A VLAN-capable switch can contain many virtual local area networks. Only devices on ports listed as members of the VLAN are able to communicate with one another. The spanning tree algorithm was created by Radia Perlman of Digital Equipment Corp. In 1985. It's an algorithm that uses a cost-based computation to compute a loop-free topology of interconnected Layer 2 switches in a single Layer 2 domain. By 1998, a standard had been produced within the IEEE to form the basis of the spanning tree protocol. This first standard for the spanning tree protocol was called 802.1d. As we saw before, each Layer 2 switch is a bridge connecting physical LAN segments. Each switch has a MAC address that is combined with a designated priority to establish an order which is used to determine the root of the spanning tree to be computed. From this root node, a computation of least costs to each node in the L2 domain is used to determine which links connecting the nodes are to be included in the spanning tree. Only the links included in these least cost paths are kept. The remaining links are disabled to affect the loop-free topology. Since the days of creation of 802.1d, many enhancements have been made to try to improve upon both the performance of and the applicability of spanning tree. This included Rapid Spanning Tree, which is RSTP 802.1w, Multiple Spanning Tree Protocol, known as MSTP, which is 802.1s, for spanning trees with VLANs, and Shortest Path Bridging, SPB, which is 802.1aq. Of course, proprietary versions have also popped up along the way. Per VLAN Spanning Tree, PVST and PVST+, and Rapid Per VLAN Spanning Tree, which are proprietary versions created by Cisco, and Juniper Networks Answer for compatibility to Cisco's PVST, VSTP. The challenge with spanning tree is that it's slower to converge in times of link failure. Standard spanning tree can take 30 seconds or more to recover from a topology change. Rapid Spanning Tree optimized this to significantly reduce topology recovery times. The other challenge with spanning tree mechanisms is that it created loop-free topologies by taking perfectly good links out of service by blocking traffic from using them. In larger topologies, this can result in a significant number of unused links. Let's see how packets are addressed and forwarded in a network. As we described earlier, just above the physical layer in the OSI model is the data link layer, where Layer 2 addresses are found. Every network interface card in an Ethernet network must have a Layer 2 MAC or Media Access Control address. A MAC address is composed of 6 bytes. The first 3 bytes typically identify the manufacturer of the network interface card, and the last 3 bytes are usually from a range specified by that manufacturer for that component type and model. Although modification of a MAC address is permitted on many devices, MAC addresses are required to be unique within specified network domains, so that communication can be supported between designated hosts. Within Layer 2 domains, MAC addresses are used to identify source and destination addresses for packet forwarding. Ethernet switches forward traffic based on Layer 2 MAC addresses. In the same way that you send email from yourself to someone you're communicating with, applications and network-attached devices need to use addresses to identify the source and destination of the communication. Typically, an OSI Layer 3 address is known as the target for the communication. A Layer 3 address is a logical network address. One or more Layer 3 addresses, so they can be IP, IPX, AppleTalk, etc., can be associated to a physical interface to the local area network. But each physical LAN interface can only have one data link Layer 2 MAC address. In order to build an Ethernet packet to send to the destination host, the Layer 2 destination host MAC address is needed. If the destination MAC address is not yet known to the sending host, Address Resolution Protocol packets, so ARP, are sent to all hosts in the LAN using a special reserved broadcast MAC address, which is all Fs in hexadecimal, in order to resolve the layer 3 address to the physical address of the remote host. If the host is in the local layer 2 LAN, it will reply to the ARP packet with its MAC address. If the host is not found locally, but is in a network attached to a locally attached IP router, the IP router will reply with the MAC address of its interface to be used as the destination layer 2 address, as it is in the local layer 2 network. In a single layer 2 domain, all hosts can be reached using the appropriate MAC address. This includes LANs, VLANs, and VPNs, as we'll see in MPLS. Each network switch, however, has to learn the MAC address of the attached hosts in order to efficiently forward packets to their appropriate destinations. Packets destined to unknown hosts are flooded to each port in the switch until the port connecting to the host with that MAC address sees the new MAC address in the source MAC address field of the response Ethernet packet. Once the MAC address is learned, packets destined to that MAC address are only forwarded to the associated port. All other ports will stop receiving packets with this MAC address as the destination. As the number of devices increase in a layer 2 domain, network loads due to packet flooding and broadcasting become a bottleneck for performance. In order to increase scalability of the network, it is separated into smaller chunks, and layer 3 addressing is employed to provide a common addressing scheme across multiple layer 2 domains. Adding an IP source and destination address to an Ethernet packet allows the creation of an IP-based network to be overlaid on top of multiple layer 2 networks. This facilitates much greater network scalability and reach. Packets can now be forwarded at a macro layer based purely on IP addresses, while at the local micro layer, MAC-based forwarding is preserved for propagation between devices attached to switch networks. When the conversation is carried out using layer 3 addressing, IP addresses, IPv4 or IPv6, will be used to identify the source and destination. Each layer 2 domain is assigned a block of layer 3 addresses, referred to as the network address. Each layer 3 IP address in each subnet resolves to a layer 2 MAC host address within a single layer 2 switching domain. Just like switches forwarding packets based on the MAC address, routers forward traffic between the networks based on the network portion of the layer 3 address. If the desired host destination is not found in the local layer 2 domain, but is in a reachable layer 3 network, the router is used to connect the layer 2 domains. As each layer 2 domain forwards packets based on the destination MAC address, the router port connected to the local layer 2 domain is used as the gateway to reach other layer 2 domains. This is done at layer 3 by assigning an IP address to the router port, which is a part of the local layer 3 network, and having all network attached devices told to use this address as the gateway out of the local network. For packets leaving the local switch network bound for a routed destination, the MAC address of the local L2 domain port of the router is used as the destination MAC address, while the destination IP address is the IP address of the ultimate destination host in the remote layer 3 network. When the layer 3 address lookup occurs on the source host, the layer 2 next hop for the packet is the router port. This is why it is used as the destination MAC address for the packet. On receiving the packet, the router will inspect the packet destination IP address, determine the host MAC address, and use this as the new destination MAC address for the packet as it is sent out the port connected to the host network. The source MAC address of the packet will be modified to be that of the router's port connected to the destination layer 3 network in order to preserve source and destination MAC addresses within the local layer 2 domain of the next hop. This will inform the destination host of the MAC address to use as the destination MAC address when creating packets to be sent back to the conversation source host. Let's have a quick peek at traffic management. How is traffic prioritized? What methods are available to ensure traffic meets service level agreements? Traffic that is injected into a network comes from many different applications with varying levels of criticality. Some traffic absolutely positively has to get where it's going in a very timely and consistent manner, and some has no time-based guarantees but is okay to be handled on a best effort basis. In times of congestion on the network, some applications are okay with having to resend data while others are not. This means that some less important traffic can be dropped or delayed in favor of the critical traffic. In order to have the network elements know which traffic is important and which is not, there needs to be a way to identify or mark the traffic of varying importance. The act of prioritization of traffic can be as simple as saying all traffic on this interface or VLAN is of this importance, or as complex as marking each packet with a reserved bit pattern to show its priority. When we want to be able to differentiate importance of packets within a port or VLAN, a priority marking bit pattern needs to be applied within each VLAN or IP-based stream of packets. The application of a marking to a packet has to take into account the nature of the forwarding capabilities of the network in relation to the type of packet being marked. As a result, there is a different marking mechanism for Layer 2 forwarding versus Layer 3 forwarding. Packets that are Layer 2 forwarded can be marked using the 802.1p bits, which are found inside the VLAN header of the packet. This is a 3-bit field that allows a value range of 0 through 7, with 0 being least important and 7 being most important. Marking each packet inside the VLAN is either done by the device creating the packets or by the network equipment converging packets from multiple priority-specific ports into the common VLAN. Marking the packets allows the VLAN to carry many packet streams of varying priorities concurrently, while enabling the network equipment to treat each packet as its priority indicates. Packets that are Layer 3 forwarded are usually marked using either IP precedence or DSCP, which is Differentiated Services Code Point. Both of these marking schemes use a common set of bits in the IP header, but use is determined by both the capabilities of the network equipment and the granularity of priority dictated by the end application. IP precedence utilizes 3 bits for priority, similar to that of Layer 2's 802.1p. It is found in combination with 5 types of service bits, TOS bits, that indicate things like delay, throughput, reliability, and cost settings. DSCP utilizes the top 6 bits of this 8-bit field to indicate 64 levels of priority, again with 0 being best effort and 63 being most important. Priority groupings within this scheme are frequently referred to as best effort, assured forwarding or AF, and expedited forwarding EF. A class selector CS identifier was assigned for values where bits 3 to 5 were 0, so that DSCP values could easily map into precedence values for backward compatibility with older network equipment not yet supporting DSCP. As you can see, this does also give a good way to align priority schemes between the 3 marking mechanisms. Application of these priorities is dependent on the relative importance assigned to each traffic flow by each network administrator. As a result, priority mapping exercises are commonly performed at network boundaries to align the relative priorities of one network operator to the next in order to preserve the prioritized importance of the transported traffic. Further specifics on the components of DSCP can be found in the Internet Engineering Task Force Request for Comments document number 2475, which can be found at ietf.org. Policing is commonly used as a mechanism to ensure that each priority of traffic flow does not exceed its contracted throughput. Methods available range significantly and include 1, 2, and 3 bucket policers, which provide alternative methods to manage the indication of how traffic meets or exceeds its contract, as well as alternative granularities of when and how the violating traffic may be discarded. Put simply, policing manages the discarding of traffic that is flowing in excess of the rates agreed to by the network operator and is usually performed as traffic ingresses a network device. Shaping is a mechanism used to delay packets within a priority flow in order to help it stay within the flow profile to which it is assigned. Using buffering, packets are queued so that packets egressing the interface towards the next network device in its path do not exceed the assigned contracted rates. Now that you have the basic terms and concepts of Ethernet-based networks, let's go through some important items presented in MPLS-TP. We'll start with how MPLS is yet another layer of abstraction. Similar to the benefits of abstraction gained by adding IP addressing on top of a Layer 2 network, MPLS allows abstraction such that multiple Layer 2 and Layer 3 networks can be carried across a single MPLS topology. Being encapsulated into an MPLS topology means that another layer of packet encapsulation is required in order to abstract these Layer 2 and Layer 3 networks into separate entities. The MPLS label is used as an addressing mechanism similar to that of the IP address or MAC address. The benefit of the MPLS label is that it is a fixed-length 4-byte field found in a fixed location in the packet, which facilitates much faster lookup and forwarding capabilities. Each transported Layer 2 or Layer 3 network is defined as a service carried on MPLS. Connections between specific endpoints in each service are called pseudowires and are identified with a label unique to that service on the network device hosting the service. For packets inbound from the WAN, the label provides a clear address identification so that the packets are forwarded into the correct local VPN endpoint. Each service pseudowire is mapped to a path between service endpoints, called a label-switched path. These paths are defined using labels on each MPLS router between the source and destination service endpoints. In this case, the labels on the routers between the endpoints form a path, like a cookie crumb trail, for the pseudowire packets to follow to the correct destination. The functionality and role of the elements involved in service delivery in an MPLS network topology behave a bit like a chameleon. Although the network units within the MPLS network provide a consistent look and feel to the network operator in the manner of core nodes being provider or label switched routers where labels are swapped, and the edge nodes being provider edge or label edge routers where labels are applied, the way the edge nodes interact with the attached customer edge equipment, or CE, is defined by the service type used. For example, in a Layer 2 VPWS service, the MPLS equipment is transparent to the service, as it has no impact on or interaction with the attached customer equipment above the physical layer. In a Layer 2 VPLS service, the edge nodes each look like a port on a switch, with the entire MPLS cloud infrastructure filling the role of the switch, complete with MAC learning. Note, although spanning tree bridge protocol data units are transported by MPLS VPLS services, MPLS does not normally have any involvement with it. In a Layer 3 virtual routing and forwarding service, each edge node looks like a port on a router, and the whole MPLS infrastructure presents as a single multi-port router to all the sites and ports in the service. In later courses, we'll go through the intricate details of how your application packets are encapsulated into MPLS packets. For this course, though, let's touch briefly on the label components of the MPLS packet. As we said, the labels on the routers between the endpoints form a path, like a cookie crumb trail, for the packets to follow to the correct destination. Following this train of logic, then, it can easily be understood that labels are directional. A label, be it for a pseudowire or an LSP, creates a relationship between where you are now and what the next hop is to your destination. Each service on the sending LER will use the appropriate pseudowire label defined to reach the desired remote endpoint. Once the appropriate pseudowire label has been added to the packet to tell the remote LER which service the packet is for, a label-switched path label is required in order to define the path to be used to reach that remote endpoint. Each flow of traffic for the services between that same pair of LERs will have a separate pseudowire for each service, but they can share the same LSP if the characteristics of that LSP meet the needs of the pseudowire services. Again, this is going to use the appropriate label to get to the remote endpoint. It has no relevance for any traffic coming in the opposite direction. Of course, this whole process, pseudowire and LSP label, would need to be used for the return direction as well. Pseudowire labels tell the receiving MPLS LER which service the packet is for. It is used by the transmitting service LER to tell the receiving service LER, the L2 or L3 virtual private network service, that this packet belongs to. The pseudowire label is also unique on the receiving LER, such that the receiving service will know exactly which remote endpoint of the service that the packet came from. As the pseudowire is only used on the LERs, it is the label entity that creates the service-specific tie between the endpoints. one endpoint as the transmitter and the other as the receiver, with the receiver being able to identify both the intended target service and the transmitting source by the pseudo-wire label. As you see in the diagram, node 3 will distinguish between which local service to forward the packet to based on the pseudo-wire label. Service A will be able to distinguish between the two remote ends of the VPLS service using the pseudo-wire label too. Now that you're familiar with labels and their significance, let's do a dry run-through of a packet flowing across an MPLS network. After that, let's take a peek at bidirectional tunnels unique to MPLS-TP and how protection is supported in the Jungle Packs. The following example walks through the packet forwarding associated with a point-to-point VPLS service. A VPLS service, as described earlier, is a Layer 2 VPN multi-point to multi-point service, connecting endpoints which forward based on the Layer 2 MAC address in the customer packet. Each pseudo-wire between the service VPN endpoints is assigned a label used by the endpoint to identify incoming packets as part of the service. Each hop of the LSP between the label edge routers is assigned a label used to form the label switched path. When a packet arrives at an access port in a VPN, a lookup is performed using the destination MAC address, and a label corresponding to the pseudo-wire termination on the remote endpoint is prepended to the service packet. This label will be used to identify the correct VPN on the remote provider edge or label edge router where the service is defined. Note that the local router on which the access port is located is also called a provider edge or label edge router, LER. Next, a lookup is done to see which label switched path, or LSP, label this packet is to use in order to follow the correct path to the remote provider edge router. Based on the label and the associated next hop, the packet would be forwarded out the correct interface to the next router in the LSP path. At that router, the label switching part of MPLS takes place. This router is known as the LSR, or the label swap router in the label switched path. The label on the ingress packet is inspected, and a lookup in the forwarding table is done based on this label to determine the corresponding port and label to use next in the path. Once the packet reaches the final router in the path, the label edge router, or LER, the LSP label is popped, and the next inner label, the pseudo-wire label, is inspected to determine which VPN this packet is for. Once determined, that label is popped, and the original service packet, which was encapsulated in the MPLS packet for transport, is forwarded to the VPN and its associated local access ports. Another important thing to note at this point is that unlike IP-MPLS, MPLS-TP doesn't pop the LSP label until the destination LER has been reached. This is part of ensuring that the LSP is connection-oriented. In order for the destination LER to know which packets are received from which LSP, the LER needs the label to identify the LSP. This is very important for another feature of MPLS-TP, OAM. We'll cover that in a few minutes. MPLS-TP introduces the concept of bidirectional tunnels. In IP-MPLS, a pair of opposite direction label-switched paths, transmit and receive, have no definitive relationship between them. This meant two things. First, there was no cohesive unit to associate the two directions of traffic flow to form a bidirectional flow. When multiple LSPs are created between two common endpoints, with each LSP being for either a dedicated purpose or priority, it is very difficult to get a clear picture of the bidirectional flow of the purpose or priority-based traffic patterns. Second, without bidirectional association, it's difficult to assure or even ascertain path or performance symmetry of the transmit to the receive paths. As MPLS-TP was designed to bring transport qualities similar to that found in SONET SDH, OTN, and other TDM technologies, it introduced the concept of bidirectional tunnels as a mechanism to create and manage the relationship between a pair of LSPs. Bidirectional co-routed tunnels are defined when two LSPs share the identical member path nodes. This assures that the LSP from node A to node B transits the same nodes as the LSP from node B to node A, just in reverse. This type of tunnel is used when node performance or reliability as well as hop counts are important. Bidirectional associated tunnels allow the association of one LSP in one direction to another in the reverse direction, sharing the same endpoints, but not necessarily sharing the same node hops between the endpoints. This type of tunnel maintains the transmit-receive relationship, but allows diverse physical paths necessary for network engineering activities such as load distribution. 1+1 and 1-to-N protection schemes are available in MPLS-TP to increase the survivability capabilities and reduce fault recovery times of MPLS-TP services. With 1-to-N protection, a primary bidirectional LSP tunnel and one or more non-active secondary bidirectional LSP tunnels are used. Only one tunnel is used at a time. In times of failure, the source needs to be alerted to change the tunnel used to send packets. This adds to the overall fault recovery time. With 1+1 protection, as is offered with the GE Jungle Packs, traffic is replicated and sent to a working and a protect bidirectional tunnel at the same time. The LER on the terminating end of the tunnel makes the choice of which tunnel to receive packets from. This means that in the event of a failure of the working path, the LER on the terminating end of the 1+1 protected tunnel pair can simply choose to receive packets from the protect tunnel. As packets are sent to both tunnels at once, there's no additional delay or loss of packets waiting for the source to transmit packets on the protect path, as there would be in 1-to-N protection. As the Jungle Packs has fully redundant hardware and 1+1 is implemented using this hardware redundancy, packet loss is protected both at the physical and hardware layer and at the logical LSP tunnel layer. The Jungle Packs utilizes an east-west architecture, creating a pseudo-ring topology ideally suited to 1+1 protection switching. We've seen prioritization in Ethernet. Let's have a look at how it's applied in MPLS. As MPLS-TP is based on a subset of the functionality found in IP MPLS, many features are executed the same way on both topologies. QoS, quality of service, is one of those features. In this slide, then, we'll refer to both IP MPLS and MPLS-TP as just MPLS. MPLS services are able to classify ingress application traffic based on the main criteria of port, VLAN, VLAN priority marked using 802.1p, and content such as DSCP or IP precedence as found in IP headers. MPLS labels encode multiple priorities as well. MPLS labels have 3 bits in each label called the traffic class bits. These bits indicate levels of priority between 0 and 7, with 0 being the lowest and 7 being the highest priority. Depending on whether the MPLS part of the network trusts the service, the priority markings of the service packets can be mapped into the traffic class bits of the MPLS labels, so that the routers doing the label forwarding can be made aware of the desired service level for each packet without having to be aware of the service itself or its contents. This allows packets transported across MPLS to be serviced using standard QoS mechanisms of classify, schedule, and remark. These concepts are covered in other modules. Let's use the same L2 VPN service as an example. When a packet arrives at an access port in a VPN, the priority of the packet is determined using predefined industry-standard priority classification schemes. In this case, the packet arrives with a port default priority equal to 4. This maps the packet into the appropriate internal priority and egress queue for priority 4. When the label corresponding to the pseudowire is prepended to the service packet on egress from the VPN towards the WAN, the packet priority is mapped into the TC bits in the pseudowire MPLS label. Next, a lookup is done to see which label switch path label this packet is to use in order to follow the correct path to the remote provider edge router. When the LSP label is inserted in front of the pseudowire label, its traffic class bits also inherit the value of 4 to signify the priority of the packet as set by the pseudowire label. This results in the packet leaving the JPAX router with the outer LSP label containing the priority of the packet. As the MPLS packet enters each JPAX router on its path towards the destination, the packet is reclassified by each router into the appropriate internal priority queue where the packet is scheduled and switched onwards based on the priority embedded in the LSP label. Each time the LSP label is swapped as part of the LSR function, the priority of the packet is remapped into the new LSP label before it leaves towards the next hop. As MPLS-TP does not pop the LSP label before the end of the LSP, all of the information in the label is preserved for use by the remote endpoint JPAX. This includes the priority of the LSP. As each label, LSP, and pseudowire are popped, QoS maps can be used to map the priority of the packet as desired on that JPAX. Note, each of the pseudowire and LSP labels are able to use priority translation maps so that port QoS priority maps can map into a distinct priority map for the specific LSP, should the LSP traverse a network not using the same priority values. For example, a service packet with a priority of 7 can be mapped to a lower value, like 4, if the JPAX network operator feels that the relative importance of that service traffic does not merit a 7 treatment through the JPAX MPLS network. This would not affect the priority marking of the encapsulated packet, but would just offer level 4 service to that packet as it traverses the JPAX MPLS network. We've saved the best for last. Operations, administration, and management capabilities and features leveraged by MPLS-TP. OAM stands for Operations, Administration, and Maintenance. The thing being monitored or measured is usually referred to as a maintenance entity, ME. This can be either a pseudowire, label switch path, or a segment of a label switch path. The two endpoints of a maintenance entity are referred to as the maintenance endpoints, MEPs, MEPs. MPLS-TP introduces a unique approach to OAM. With MPLS-TP, OAM packets for measurement and monitoring are carried in the LSP and pseudowire or service that they are monitoring or measuring. In most cases, when packets are sent from one endpoint to another, they are sent using the generic associated channel, which uses the reserved MPLS label called the GAL label or generic associated channel label, which has a value of 13. As an example, if the maintenance entity is a pseudowire using the green labels, the OAM packet is created with the pseudowire and LSP labels with the OAM label as the innermost label. Note that the LSP and pseudowire labels are the same as the packets in the VPN, so that the packets are received on the same VPN endpoint as the VPN packets. This is what guarantees treatment that is fate shared with the packets in the VPN pseudowire being measured. BFD, or bidirectional fault detection, uses the GAL label as the innermost label when associating BFD packets to a specific LSP or pseudowire. The GAL label is set as the bottom of stack label inside the pseudowire or LSP label as appropriate to what is being monitored. BFD packets are sent at preset intervals in order to monitor the maintenance entity for detection of connectivity faults. As a default, BFD sets the loss of 3 heartbeat packets as the minimum BFD detection interval, but this is a configurable parameter. In addition to BFD OAM packets, which are CC for connectivity check, CV for connectivity verification, other OAM packets, such as LM for loss measurement and DM for delay measurement, are used to provide performance measurement capabilities. The big benefit of MPLS-TP is that these OAM packets are fate shared with the LSP or pseudowire that they're measuring. Unlike IP-MPLS, where you have to build a parallel service to simulate the connectivity you're trying to measure and potentially install extra equipment, MPLS-TP requires the ability for OAM traffic to be generated inside the entity being measured. Whatever forwarding, quality of service, filtering, etc. happens to the VPN packets as they traverse the pseudowire will also happen to the OAM packets. In this module, we covered how Ethernet packets are constructed. We also touched on Layer 2 and Layer 3 packet forwarding, MPLS-TP virtualization, how payloads are encapsulated and forwarded in an MPLS network. We looked at traffic management, and we covered OAM in an MPLS-TP network.